Topic 13. Deformation of solids. Part 2. Stress and strain. Stress. Tensile stress, as illustrated here. This is the tensile force per unit area applied to a sample of material, like here. Force must be perpendicular to the area, to this area here. Tension T may be used instead of if. Tension is simply the force applied to a string, a rope, or a wire like this. Stress. Symbol for stress is the sigma here. And the formula for stress is sigma equal to tension or force divided by the area. The SI unit is Pascal. Derived unit, you can do that yourself. Strain, tensile strain. This is a piece of wire. Its original length is here, L. And under the action of this force, F, it is extended by this much. So X is the extension. It says here the change in length, X, per unit length, L, which is the original length, of a sample of material. More on strain, tensile strain. The symbol for strain is this fancy E. It can also be written like this. Now the formula for strain is extension over original length. SI unit, no unit, since it is a ratio of two lengths. Some quick questions. Question number 1. Does the extension of a material depend on the original length? Question 2. Does the strain of a material depend on the original length? Young's modulus, or sometimes just Young modulus in some books. Symbol is this capital E. Modulus is equal to stress divided by strain. The unit is Pascal, same as stress, since strain has no unit. Derived unit, I'll leave it up to you. Young modulus formula expansion. Expand stress and strain in the formula, then simplify so that there is only one divide line. Here it is, modulus equal to stress over strain. Stress has this formula, strain has this formula. Simplify this, you get that, which is a useful formula. Read through this example and calculate the Young modulus by using this formula. Stress and strain graphs. Here we have two line graphs, each one representing a different material. Label one hard material and the other soft material, and find out which is which. Now the gradient of the line gives you Young modulus, Y. Think about Y. Word definitions. The definitions of these three phrases. Now look at this graph here, which is stress versus strain graph. And you can see that it looks similar to force versus extension graph. First of all, the straight line part is called the elastic deformation. The curved part is called the plastic deformation. And the maximum stress is called the ultimate tensile stress. Now we're looking at structure of solids. Materials can be distinguished in terms of mechanical, electrical, and chemical properties. This, however, does not always work for all materials. There are always exceptions, in other words. The most important classification that deals with the arrangement of particles in a solid is a science called crystallography. The first type of structure we're looking at is crystalline solids. And here is a pictorial representation. And here is a diagrammatic representation. Particles show a regular arrangement with well-defined patterns of three-dimensional arrays. like this one here. Examples are many minerals. The second type of structure is called polycrystalline solids, as illustrated by this picture and by these diagrams. A large number of small crystals form a regular pattern, for example, most metals. This regularly repeating arrangement is described as long-range order. In other words, there is no short-range order. The third type of structure is called amorphous solids, like this one here. Its meaning is without form. Amorphous means without form. Short-range order only, and you can regard it as distorted crystalline structure, for example, glass. The last type of structure we're looking at is that of polymers, like this one here. They contain chains of monomers which are regularly repeating units, usually carbon or organic compounds. Polymers can have both crystalline and amorphous regions. There are two types of polymers. The first type is crystalline polymers. They are strong and rigid. Examples are nylon and polythene. The other type is amorphous polymers. They are soft and flexible, like rubbers. Now we're looking at stress and strain graphs for different types of material. The first type is ductile material. Ductile means being able to be drawn into a piece of wire. So many metals are ductile, like copper, for example. If you get a piece of copper wire, say, and apply force to it, then it will stretch along this line here, pass elastic limit, eventually into plastic region. And then if you remove the force, it will come back along this line. It will not go back there. So it is now permanently stretched by this much. You can also think about the significance of area under the graphs. Don't forget to study the definition. The second type of material is brittle material. This type of material has only the elastic region and has almost no plastic region. It will snap suddenly there. Examples are glass and concrete. And don't forget, study the definition. The third type of material is polymeric material. And this type of material has a unique stress and strain graph. When you apply force to it, it will stretch along this curve. When you remove the force, it will come back along this curve, back to the original length. A good example is rubber band. And study the definition. Also look at the significance of areas under the graphs. The pieces of apparatus used for Young's experiment, just for your general interest. Different examples of stress and strain in everyday life in their related graphs. Stress and strain, tension and displacement or extension.